shit straight, cuz. Let me do my physics homework. Oh my god, that noise is horrendous. I gotta figure out how to do this better. That's a horrendous noise. How do I escape from this matrix? I did not record. Okay, I was doing that. About to go back to my. It's probably not gonna let me come back in. You're not getting my password, buddy. I know your games and your tricks. No. I know your games and your tricks, buddy. You want my password? Think again. Think again, buddy. You're not getting my password. Actually, I don't want to test anyone out there. I believe you could get it, okay? I believe you are smart enough to get it, whoever you are out there that it's like, bro, I can't do what? Huh? I don't want that, okay? I don't want that at all. About to get some tea real quick. I'm at 50. I got through this whole thing last night. I have a 2-hour video from last night, but my audio was messed up. How unfair is that? 2 hours of horrible audio. That's what happens when you start doing this. First, launch the video into displacement vectors and adding vectors. This is from last night, but we're gonna continue and just keep moving forward. Displacement vectors. Displacement vectors. I know where to displace your vector. Displacement vectors. I know where to place your vector. All right, let's listen to bro. I'm gonna turn this down because it was too loud last time.
So what do we mean by displacement? Displacement is moving from one location to another. So if you think about moving in a 2-coordinate system, X and Y, a 2-dimensional system, we need to know a couple things. We need to know where you started and where you ended.
Okay.
So let's say you started there and you ended right there. How would I define those positions?
Oh look, guys, I know I just started the video, but I'm about to grab my tea because that kettle is killing me right now. I'll be right back. She's saying I'm too nonchalant. Too nonchalant. All right, let's go. Let's go.
This coordinate space. The vector from the origin to your initial location is S sub I.
S sub I for initial. Let's go do some cool stuff here. Boop, boop. Dude, let me draw. There we go. So this is my initial location here at the origin. And this is my vector indicating where I came from. S sub I. We're going to pretend like that's a sub. Or I could just make it a capital. So how do you make stuff sub on Windows? And then we can draw a little dot. Let me see. Not dot, arrow. This is my vector S sub I. This is direction from the origin I'm going.
The vector from the origin to your final location is S sub F. And therefore, delta S
sub F. That's your final. There's going to be someone like, dude, why don't you just copy the video? Because I'm not a copycat. Okay. I want to understand it on my own terms. All right, so this is the initial starting point, the vector, and this is the final position. And then we gotta do a little thingamajigger. And this is our vector.
Is going to be the difference between the two. It's going to be the final location minus the initial location. And we know exactly what that should look like. It should look like that right there. From where you started to where you ended, that's what delta S looks like. Now let's convince ourselves that this is true based on our rules for vector addition. So one thing we said was, if you are subtracting a vector, it's exactly the same as adding the negative of that vector. Okay. SF looks like this, up and to the right. SI was up and to the left, which means that the negative of SI, you just flip the arrowhead. Okay, same length, just opposite direction, so it would be down and to the right. So it would be something like that. And now I'm just adding two vectors. How do I add two vectors? I start at the beginning, I go to the arrowhead on the end of the last one. And now that delta S, which is roughly how we drew it over there, is that long and it's in that direction. Okay? So adding vectors means this tip to tail method applies, and anytime you subtract it, you're really just adding the negative of it. And here, let's talk about adding vectors when we have more than just two vectors. And let's say we have a whole bunch of them. Let's say we have vector A that looks like that, vector B that looks like that, vector C that looks like that, and vector D that looks like that. Okay, they each have a length, that's the magnitude of the vector, and they each have a direction indicated by the arrowhead. All right, how do we add these things up? Well, let's write down the resultant vector R, which is the sum of those things. R is equal to A plus B plus C plus D. And now let's think about how to do this graphically. All right, what we said was when we're adding two vectors, we just draw the first vector somewhere. There's my first vector A, roughly the same length and the same orientation. And then I take the tail of the second vector and add it to the tip of the first vector. So there's the tail of B attached to the tip of A, and it's heading off to the right. And now we take the third vector and we move it into position such that it starts at the arrowhead and moves off in its particular direction, roughly like that. And then we do the same with vector D. Starts at the end of C and goes up in that direction. Okay, so what does R look like? R, you start at the very beginning of the problem and you go to the very end of the last arrowhead. So R is that little arrow right in there. And that graphically will now allow you to approximate what the length of that vector is going to be and what angle it's going to be. And so you can double check with your calculations when you're all done.
Very cool. Very cool. All right. So I'm just going to reiterate some like cool, simple stuff that I want to get into for myself. So this right here, this delta vector s final minus f s initial is the general formula for displacement. So displacement equals a vector final minus the vector initial. And it's super simple, but this triangle here is delta, and that's just the Greek symbol for change. And yeah, I have a bunch of notes from yesterday, but we're gonna get into that later. So far we're just gonna get to the questions and see if I can think through them. I'm doing way better. I did way better last night because I was like super sleepy for some reason than I'm doing right now, and like just thinking generally. Let's see. A particle's initial location is given by the vector s initial 1, 0. This particle's final location is given by s of sub f final 0, 2. What is the direction of the displacement vector delta s? Delta vector s. So it's just this here. The direction points upwards and to the left. Let's actually just do this, because I don't see any value in just getting the answer right. This is meant to be deliberate and slow. Slow is smooth, smooth is fast. So that's what we're going to do here. This is the initial position of this vector. A vector is just a magnitude and a direction. Our vector SI here, initial position, and it goes to the endpoint at SF. This is our resultant vector here from connecting these two vectors. So you have R sub, you just have the R, which equals SF minus SI. And this goes upwards and to the left. So do it like this. Add a little arrow there. And that's what we have. Boop. Let's see if that works. Boy, oh boy. I gotta get a new a separate table for my mic. Every time I put the T down, it makes a large noise. Let me go to the next one, dude. You see? Do you see? Oh, am I done with that one? Okay. The vector A, which is shown in the figure, has a magnitude of 10 and a direction angle of 60. degrees. What is the magnitude and direction angle as measured as counterclockwise from the positive x-axis of negative a divided by 2? I've never done something like this. Let's let me what? Words and numbers, bro. Words and numbers. That's where they get you, man. What I'm gonna do is make this easier on myself. So let's do this deliberately. We have our givens. Our givens are vector A has a magnitude of 10. Vector A, A equals 10. And a magnitude is just the length of a vector. A scalar length of a vector, and a direction angle of 60 degrees. A direction 60 degrees. I don't know how to do a degree symbol, but degrees. What is the magnitude and direction angle as measured counterclockwise from the positive x-axis of negative a divided by 2? So here's the cool part. What is I believe it's asking is so basically this is a. If you flip a, that's the negative. It's here. If you flip a going in that direction, that's the negative. It's asking us to get the inverse. So to get the inverse, I think something really cool. If it's above 180, you subtract 180. If it's below, you add. So this would be 240. 240 degrees from the positive x-axis. So it would go like that. 240 degrees. 240 degrees and divided by 2. Divided by 2, the magnitude would still be 10, making it negative, but divided by 2 would be negative 5, 240 degrees. I want to say that sounds right, but to go into further detail, let's go into further detail real quick. So what we're gonna do is we're gonna make a Cartesian coordinate plane. We're gonna make a Cartesian coordinate plane, or in quadrants. So this is how the angle is measured here. Let me see. 2. All right. So angles on a quadrant or a coordinate plane like this are measured from the x-axis counterclockwise. Right? So that means it's going like this. It's starting from the positive x-axis and it's going counterclockwise around this entire thing. Now, what we'll notice here is that each of these has a right triangle, right? You have one here, here, and here, here. So you have 90 degrees, 90 degrees, 180, 180, 270, and 360. Right? 360. So I know we had our rule about plus or minus 180 from before to get the opposite of what we were trying to find in regards to 60 degrees. Right? This was 60 degrees. Let's just put that. But we know it's opposite. We know that it would go into the third quadrant, right? So we know, even if we didn't know the rule about plus or minus 180, we would know that the answer would fall in between 180 and 270 degrees, right? So the only two answers that fall into 180 and 270 degrees are both 240, right? And we're cutting it in half. The magnitude, I am wrong about the magnitude. Am I? I want to say no, it's still -5. I may be tripping. Okay, I'm gonna tell you guys exactly what I'm thinking, because it's probably the reason why I'm wrong or right. But the magnitude is always like a positive number. Like, just because you're making the vector negative, that just flips the vector. The length can't be negative technically, but relative to a direction, it can be negative. But it says, what is the magnitude and direction angle? I want to just say 5. Honestly, I might have been right with -5, but I want to say 5 to 40 because a magnitude can't be negative. And I'll just take the L. Okay. So yeah. So my thinking was they kind of this is just this negative here applies to the direction, but if you can't, like, in real life, you can't walk a negative distance. You only really do anything negative or positive from some other reference point. And that's really how positioning works on a coordinate system or just in real life. So this is for me and you guys or anyone else, gals. So for any position, you need an origin or point of reference origin, point of reference. You need a distance you're going to travel, which is the magnitude, and you need a direction, right? But the origin or point of reference is what gives us our negative or positive. But this is just a floating vector with no real reference to anything else. No. The magnitude is still going to be positive regardless, and the direction is going to be negative because you can't walk negative space. Like, there's no way to like do it. So like these arrows here don't mean anything because the magnitude is still what it is, right? So imagine you just do the line of this vector in the opposite direction. So this is the 60 degrees here, and you just draw a line without the arrow here, indicating the new vector, inverse vector. If you don't put the arrow, you just have a line, and the magnitude is the length. And when you put a line, that's when people start then when you put the arrow, that's when people start saying negative or positive, but the magnitude is still what it is. That was my thinking about it. Find the magnitude of vector A sub 1 represented by the pair of components AX. So we're gonna always start from what we have, no matter if you can do the math or not, just to make a habit of it. Our givens are A1X. A1X equals negative 8.8 centimeters, 0.8 centimeters. A1Y equals 5.77 centimeters. And it wants us to get the magnitude, which is the length of vector A1. But first, we're going to get into what components are, because I did that in my previous video, the one I had the messed up audio. But it was unfortunately scrapped. So here we're going to do. We're going to draw a quick coordinate plane. And we're going to make up where this might approximately be. So if you go in the negative direction, 8.8, do the highlighter. You go in the negative direction, 8.8, and you go in the y direction, 5.7. This is what you get. All right. So our vector looks something like this. What the freak? Right. And this is the final from before. This is the initial and final again from before. Now I know I centered this vector. I started this vector from the origin out of convenience, but it doesn't necessarily have to be that way. But I'm gonna put these back, but I'm just showing something. We're gonna ignore this stuff real quick. And what the components of a vector are its parallel direction points to the axis of the coordinate plane. So this right here would be AX, the component X of vector A here, A1 here. This would be component Y of vector A1. The parallel direction for the axis, which is like rise or run. Now, if we go back, we're going to start from where we were. And now it's asking for the magnitude, which is the length of the resultant vector A1 of these two components. Now, breaking this vector into these two components is something called decomposition, but we're just going to solve the problem for now. So the formula for the magnitude of a vector is basically the distance formula. So the formula for the magnitude of vector A1 is going to be equal to the length of its x component squared plus the length of its y component squared, and get the root of those two. So it'll be like this. Here, here. A1 x squared plus A1 y squared and that right there is this. Now they're both already in centimeters, and this is going to be positive. Like, even with the given math, you can see why the magnitude is always positive because of this distance formula. Anything squared is positive. You have two squared numbers over a radical, it's going to be a positive number. So now all we have to do is substitute component x and component y for this equation, and we're going to get what we're looking for. We can get A1 equals, oopsies, equals A1 equals negative 8.8 centimeters. Centimeters squared plus 5.7 centimeters squared. We're going to plug this into a calculator, and we're going to get the magnitude here. Let's see. Squared plus 109.93 e to the radical equals 10.48. So I got 10.48. Actually, we're going to be specific, and then we'll break it down from there. Just in case. 10.48, 47, 50, 8316. This is what I got, but I'm just going to put it to 2 decimal places and hope they rock with that. Okay. So now it wants us to find the direction of the vector A1. This is our vector A1. A1. 1. So here's what we do know. I'm gonna start again from our givens because I'm a little confused where to start here. So that's a good thing that I should know, like, boom, reassess my variables. And do my givens. Now we have a magnitude of 10.48. So we know this hypotenuse is 10.48. All right. Now treating this like another given is something really simple. It has the components of a right triangle. So what we're going to do is we're going to show that this is a right angle. The x component and the y component create a right angle. So we know this angle here is 90 degrees. Here, 90 degrees. This angle's 90, so it's asking us for this angle here. It's asking us, what is this here? Counterclockwise for the x-axis. Do we have anything else? Oh, we do have. So we have, I forgot, we have this as well. A1 x equals negative 8.8 centimeters. And then we have A1 y. Why? Why? Why am I doing math on a Saturday? Not playing. Why not? Why not? Why not? Okay, let's go. All right. And we got 5.7 centimeters. Now from here, we can use a trigonometric function. To find out the angle theta. So if you guys remember the trigonometric functions, you know that, or you may not remember, so I'll just reiterate them. The trigonometric functions go like this. You have sine, so, cosine, ca, I'm gonna say what this means, ca, tan, Toa. Boop. So ka toa. So ka toa. So ka toa. How I remember it is it sounds kind of like Samoan to me. Like I'm about to dance and have like a tiki torch. And I just never forgot it after I said that. Soka toa, soka toa, soka toa, soka toa, so. That's how it sounds, yeah. And what this stands for to get sine is a trigonometric function. It opposite over hypotenuse, adjacent over hypotenuse, and opposite over adjacent. Now, all of these are the reason why these are so cool and how we're going to find our angle is all of these opposite hypotenuse are just positions from the origin or reference of our angle. And these are sides, right? So the easiest one, I would probably do hypotenuse and opposite. So I would use sine because I don't have to deal with the negative. So this is our angle. We're referencing it here. So our opposite here would be A1, Y, from this reference angle. This is our reference angle. This is the opposite side. So this is the opposite. This is our hypotenuse because it's the longest side. So it would go sine theta, sine theta, sine theta, sine theta, sine. Oh my God. Sine theta, sine theta. All right, sine theta equals opposite 5.7. 5.7 divided by centimeters divided by 10.48. All right. Now we need theta. So how do we find theta? Well, I can tell you what we can't do. We can't divide by sine to get under this to get theta because sine is a trigonometric function, not a standalone variable. So theta is integrated into sine. So what we are going to do is get the inverse function of sine that returns a value for theta in degrees, right? So we're going to make sure our calculator has degrees. So the inverse function of sine is arcsine, which you can write as sine to the -1, or what it sounded like, or you can write arcsine, just like that. And then we'll just put what we know sine is, because we know sine theta is 5.7 centimeters divided by 4.8 centimeters. All we have to do is put that into our inverse function. So we get, no, what's that? We get arcsine. It'll be sine -1 on your computer. I just don't want to draw on your calculator. 5.7 divided by 10.48. Like that. We got this arcsine. All right, we got 5.7 divided by 10.48. So I got this big number, 32.949 056 405, 73. And we're just going to put 32.95 because it rounds up. 32.95. No! No! Oh my god. Find the direction vector of A1. Of the vector A1. Where did I go wrong? It's opposite over hypotenuse. 5.7 over 10.48. No. No. Express your answer in degrees. I'm in degrees. Find the vector. Find direction vector of A1. Direction of the vector. Wait a minute. Oh, man. See, guys. Counterclockwise from the x-axis. I found this angle, right? So, here's what I messed up. I stopped at this angle. This is not the angle counterclockwise from the x-axis. So we're gonna go into what we did before. And I'm gonna save this number. I'm gonna stow this number that I just got, this really big number here. And this is 180 degrees, right? I remember we talked about it earlier. So this angle from the positive x-axis is 180 minus this angle here. So that's our answer. 180 minus 147. Let's see. Players make mistakes too. 943. 594. 27. So I'm just going to put 147.05. If this is wrong, buddy. All right, find the magnitude of vector A2 represented by this pair of components. We're going to do what we did before. We're going to do our givens and we're going to draw it. What are my givens? I'm giving every day. AX2. I'm just going to put X equals negative 3.6. 6.3. We're going to do X equals the A2 component X, the X component of A2. I'm just saying that out loud. No. I'll do it. I won't be lazy. I'll do it. 0.3 meters. I like rewriting things. I know I don't have to, but I like to do it. Negative 1.5 meters. And I forgot to do this on the other ones, but we have to show what is our target. What are we looking for? We're looking for magnitude. in meters. Good thing our unit is already in meters. So now let's draw it. We're going to make ourselves a little Cartesian coordinate plane and start from there. So we have doesn't need to actually be that. We have negative, the x component of vector a2 is negative 6.3. So it's going to the left. Right? So we're going to go and do that. We're going to go negative 6.3. And then we're going to go negative, and the y component, negative 1.5. So our vector would look something like this. Right? Right? And now we're going to just gonna do what we did before. We're going to show the length of both. Now we just substitute these into the formula for magnitude, which we know is the x component squared plus the y component squared under a radical. So we do the magnitude in meters of A2, vector A2 equals negative 6.3 squared plus negative 1.5 squared under the radical. And we're going to see what we get. I got 6.476109.94348. That's what I got. So let's put 6.5 meters. Now we're gonna find the answer in degrees. Luckily for us, this time we actually did the thing and made the triangle with the components first, with the stuff. So we're gonna put 6.5 meters. I think yeah. So we're gonna do opposite over hypotenuse. Negative 1.5 over 6.5. We're gonna do arc sine. Next, we'll keep it stupid simple. Keep it stupid simple. Sine theta. Sine theta equals negative negative 1.5 over 6.5. Works. And now we know that this is sine theta. So to get theta by itself, we have to do the inverse of sine, which is arc sine, and then plug that to the calculator. We do arc sine negative 1.5 divided by 6.5. And then we're going to make sure oops, didn't mean to do that. Calculator, stop it. I don't want it. Later is in degrees. This is a reminder to me. All right. Arc sine equals negative 1.5 divided by 6.5. And I got negative 13 point, negative 13.342.363.79709. All right, this is this angle here, like that. So because this is our reference angle and this is negative, right? Here's the cool part. This angle is negative, but it's asking us, ow, oh my God, bro. Athena, come here. Get up. Ow, bro. What the fuck? Dude, what are you doing, man? What are you doing? You don't need to scratch me to get my attention, okay? You have my attention. Now. Where did my mouse go? Well, I got discombobulated by my cat. All right. You want downsies? Let's go. All right. So now we're going to write this number. So yeah. So the angle is negative 13.34. But because it's from the positive x-axis, the angle is going to be positive. This is where the action goes. All right. So it would be this number plus our reference here, our reference at the origin, which is 180. And you'd get 193.34. Stop it. Can't chew ibuprofen. Okay. All right. Now we're going to do another one. I'm going to take a quick break to find my mouse for a second, and we'll get right back to it. Where did my mouse go? Athena, what are you doing, man? You gonna talk to him? Go ahead, talk. They love you. They love you. Dude, did I launch it? Where'd it go? It'll show up. All right, so this is gonna be a little bit harder because I don't have a mouse right currently. Uh, but the show must go on. So we're going to look into the next problem. So we have our givens. We have A3 equals the x component of A3 is 7.05. 0.05, and the y component A3, vector A3, let's be specific. Vector A3 is negative 2.5 kilometers, negative 2.5. Right? And then we have, what are we looking for? What is our target? Target, we, magnitude in kilometers. Here's something that I didn't touch on before, but I think it's really cool when we specify that we know what kind of unit or thing we're looking for based off of what our target is, right? So if we were looking for speed, we know our result would be a vector because speed is a vector of length and time, right? But because we know we're looking for a magnitude, we know our result is a scalar. That's just a random thing I just thought of, but yeah. So we're going to continue here, and we're going to do the problem. We're going to draw it out. We don't need the Cartesian point right now So we're just going to just draw it without the Cartesian plane, because they're not necessary for these problems. 7.5, and you have -2. It's going that way, and you have -2.5. And then all you gotta do, oops, just copy these. Copy. Athena, sit down. Okay. You have -2.5. That's actually the y component. And you have 7.05. And this will be a vector here that we're about to draw. You'd have it go from here to here. This is your vector A3. All right. To find a magnitude, all we need to do is square the x component and add it by the squared y component and get its radical. Again. Three. A3. And you would do 7.5 squared, 7.05. The order does not really matter. Plus -2.5, 2.5. And this would be your magnitude for vector A3 here. Okay, now don't sit on the laptop. You're okay. I'm not mad at you, but do 7.05 squared plus 2.5. You can put the negative you want, but it's going to end up being positive anyway. And that gives you 7.480,140,373,01 kilometers. And we're going to put 7.5. Ouch. All right, now find this in degrees. All we have to do is remember 7.5 km here. 7.5 km. Remember that our reference angle, now we can have a little X and Y. You know what I'm talking about? We can, you know what I'm saying? That's just showing us that we're somewhere in the we're going from the origin. This is our angle. Might be a better idea to move this. I'm just trying to make this make sense. It doesn't even need to be like that, but okay. Now, all we gotta do is remember that the angle here is what we're going for. And remember SOHCAHTOA. So right now, we could just do sine again. Sine over hypotenuse is opposite over hypotenuse because this is the angle here. And do negative 2.5. Equals negative 2.5. And after I finish this, I'm going to stop the video and continue a little bit later. Negative 2.5 divided by 7.5. And then we are going to get the angle by doing arc sine again. Negative 2.5, 7.5. And let's see what we get. I got negative 19. Negative 19. 19.471.220.634.49. All right. Now, because we're adding this, we're going south from the western x-axis. This would be 180 plus this number. All right. So if you put it in a calculator, you could just this number minus 180. Minus 180. And I got 199.47. Oh, hold up. Wait a minute. Uh-oh. Oh my God. Wait. This is wrong. This is wrong from the jump. Oh my God. This is positive X. Dude's tripping right now, bro. Tripping. You see, everybody makes mistakes, man. Wow. Yeah. Well, that. Put that there. And this. Well, that. That. And this. Delete that. And this. Put it here. That. There. So I'm thinking like you can just inverse this. This is trying to take the easy way out here, but I'm thinking these would be the same angles, just inversed. So this would just be 19, and you could subtract 360 from this. 360 minus 19. 340.53. Yes. All right, I'm about to stop the video and we're going to come back later.